resolution. And now for the residual and the inception.
它等于
Yeah, let's take a residual. So this is RES stands for residual. So in Chinese, that is the residue. Right? The residue. So that's easier. So it's easier to learn the h of x from the f. We take the difference in the difference instead of the h of the x by itself. So this is a concept like gradient boosting, residual, residual. This is like extreme gradient boosting. They also use the residual, the extremely gradient XG boosting. The extreme. Extreme gradient boosting. It's pretty similar concept. So you define it as a residual block. The value, so f of x plus x, then we identify x and take the residual block and to predict what is the h of the x. And inception, so gonna skip that. This is inception. There's a movie. There's a movie star called Leonardo DiCaprio, right? There's a movie called Inception, right? So yeah, Inception. That means this is ignition. The Leonardo DiCaprio. The filter with the multiple sizes, 1 by 1, 3 by 3, and 5 by 5 combo, and finally just collect them by using the multiple terms of the 3 by 3. The larger kernel like this. For information distribute more globally, so going to distribute so like this, more globally. And use a smaller size for information distribute more locally, like the local refinement. So I think I out of time. I should no, I just skip it. I don't have time. So. Dense net. Yeah, okay. I just briefly mentioned the dense net. Dense net net each layer for every other layer in the feed-forward fashion. For each layer, the feature map of the all preceding layers and use the input. So you can see that it's quite similar. So if use a composite, so size reduce, use a pattern to restore the image size. So they call it dense. So each layer is quite dense. There's a full of the hidden layer, and for each layer, the feature map of the all preceding layer is used as an input. So this is quite corresponding to each other, and its all feature map are using input into all the subsequent like this and go to. So the convolution next. Already go to the example, I think. 1D CNN. This is for time series data. Like there's a 1D data, so might be there's a 1 year or 2 year. Like for each year, you're going to have a 365 days. For 10 years, going to 3,650 data. So going to determine what is the sample size going to use a large filter to find out what is the pattern. The pattern. If they use a larger filter, the pattern. So this is like a cycle. This is increasing, or this is decreasing. This is called a pattern, right? But sometimes if it is like a hiccup, sometimes or a hiccup, or sometimes it drops down. So we use a smaller filter. So it's called a responsive. No, not responsive. We call it the pattern or the RAM. No, relate to not out that responsiveness. So take the global average pooling, and take the global average pooling. So the convolution, this is for combo. So like, so this is 1D horizontally. So we fix the combo, let's shift a little combo. So there's to investigate more global views. So if we use the smaller filter, so we're going to detect more of the smaller changes, like the combo since a smaller stripe, not smaller field.
老师，请问是所以在不同的东西跟不同的方法，一开始就要先去做分辨。
Yeah, of course. Because otherwise you never get success. So don't do blindly. So we just use CNN. And however, there's a time series. For time series, is LSTM. It's a proof for time series and 1D CNN as well. So this is like a multiple inception time or inception input multi-series, like with the human body when you go to the health check. So we check what? With the blood pressure and your impulse and some signal of your to the cardio, they're going to produce a different way, right? So going to multiple. So not only the multiple, so for the health check, it's going to generate the time series, the multivariate time series data, right? So however, yeah, it's quite genius collect like this one, the green one. Yeah, this is, look at the horizontal, this vertically. So this is a habit. This is some data related to impulse, related to the cardio, related to the low pressure, high pressure, and so on and so forth. So for different time series, however, at a particular time. So just this is a bottleneck, consider it a bottleneck, like a building truck, and build it, and something like that, and build it. So the convolution is done by this manner. So sometimes you just convol this way, convol this way, and then finally do a convolution concatenation of the multivariate time series data. So going to output. So today I use a Morris fan last 3 months. The last 3 months data for me. I would like to predict what is next week. My heartbeat, my impulse, my high pressure, low pressure, or something. So going to generate, simultaneously generate what is next week for me. This is for my heartbeat, do my cardio index, the high pressure, low pressure, something like that. So, okay, gonna skip inception. Okay, this on geometry. This is only for your reference. So I would like to. Okay, there's another thing I'd like to mention. This is quite interesting. The time series with a multi called preprocessing. Preprocessing means we're going to process the data before they fed into into the model. The data cleansing. Not data cleaning, no, we call it data cleansing. This is quite a terminology used in machine learning. And like this, I zoom in. So this is the original profile. Original profile. And so original, this is a high frequency. Use a smoothing. So how can we get a high frequency typically? How can we get the high frequency data? Use a wavelength, the wavelength decomposition, transformation of the wavelength. So we generate multiple different transform the profile into as an input. So the high frequency, low frequency, and anything else? Independent component analysis. ICA, or there's a EMD. Empirical mode decomposition. EMD, so from to high frequency, low frequency, and finally another residual like a white sequence. So you just extract the high frequency. So it can be done by smoothing. Just smooth. Use the moving average only. Take the, for example, moving average of the 3 period, the MA3 or MA5. So the average, the 1, 2, 3 as an average, and 1, 2, 3 average. So smooth order. But downsizing our the low frequency, we only take average, for example. So take this, take the average one data. Take this, one average data. Take this. So call it downsizing. Right? Okay. So this is high frequency, so we just take the smoothing. Second is the downsizing. This average take it. So originally maybe we have a 200, so downsizing into the 40. We take the 5 as average and as a represented level. So downsizing from 200 down to the 40. So just into that, and so this is a convol and concatenate, convol, pull in, fully connected, and so on. Then, okay, example Keras. Yeah, this is called MNIST. So this is data called a written character example. The sample 25 times. This is so early, right? So if you're a human, can you imagine you made a mistake? No way. Even though like this. 3. Yeah, easy for human being to identify 3. However, for computer, not that easy. For this three, yeah, that's great. Sometimes you can identify as A, right? Then A can be considered as a 3. So who knows? So number of classes total, you have about 10 classes, the digits starting from 0 to 9. And the number of training 60 and 1,000. The 6,000 and the 1,000. So, well, this is another avatar for the model representation. The model structure. Okay, another thing called the data representation by the autoencoder. They also use MSE, so I will call the reconstruction area. So that will be addressed later, okay, in the later session. Model structure, layer, dense, drop-off, dense, drop-off, dense. So this example, this is unit and the value and what is dropout rate. Originally used in the hidden layer earlier is a larger dropout and the later is smaller dropout. And so max, why we use so max, right? The input image classification. So we use a categorical cross entropy. Right? So the optimizer add-on, the typical add-on will be good. And the categorical cross entropy, why is categorical? Since there's a label, right? And batch size 200. Well, why the 200? So it's a 28. The size at 28 by 28. 28 by 28. Yeah, 28 by 28 is size. So it's a 200 and the epoch, so we have 10 epoch. For each epoch, we're processing all the batches. And the learning rate typically 1.0 exponent minus 3. Yeah, this is a code. I'm gonna skip it and okay. There's something I like you to show. You need to show this to me. You need to draw. You need to draw this. Yeah, like this. You need to draw this for me. What kind of model? What kind of combo? What is the structure you use? Right? Use the structure and then you show your written report. And then to show me, you show me what a parameter you use in the model. So you're going to show me what a parameter you use in the model also. So this is, yeah, can output. This output from Keras, right? Right, correct? Yeah, it can be synced from Keras, right? The print data, more information. And the optimization parameter setting. So yeah, there's a scikit-learn. There's a tool inside optimize the add-on optimize something. So we go to yeah, there's some built-in function for you to for your perusal. And then start training. And then evaluate the model accuracy. So first of all, you need to look at convergence plot. The loss function. So look at the convergence during the training. So if it is okay, then we proceed to the testing. Otherwise, don't print it out for the testing result. You need to make sure your algorithm converges. Converges, I mean the structure. No, the data has been well represented by the model choose. Otherwise, no, the prediction will be a disaster. Then conversion plot and maybe do the validation. This is done by hyperparameter and the testing. And the testing, we're going to do the confusion matrix. I can use a recall, use the accuracy, like accuracy and the precision, and f.5, f1, f2.0, and false positive rate or false negative rate or something. Yeah. Right? There's several statistics you need to do, and perform the analysis. Then, so evaluate model accuracy between the testing result, and then build a confusion matrix to observe the results. Question? I think they're quite straightforward, right? Yeah, I know. If you need more time, just let me know. Just like me. Personally. so say, yeah. So I can communicate. Yeah, don't worry. If you need more time, I'm okay. Right?
你需要附上 code 吗？我没有。
放附录，再附录。
Yeah, sure. Yeah, append your
放在
code. Yeah.
后面。
Yeah, append your code. So I can do the comparison. Wow, copy his code. Yeah. Yeah. So hey guy, yeah, don't be afraid to talk to your friends or colleagues. So you can communicate to exchange idea. When you get when your question or your a skepticism has been solved, you just go back to do your own work. So I think it is totally understandable. So it won't lead to the pressurization. They don't. So you cannot produce exactly 100% as the other. There's no way. So you just write your own report. You understand?
有问题的话，找光伟这边会
一家会。
接受。
Hold on, I still have something to say. And DNN for regression, so this is not example. Only for example, in practice, the practitioner never try to desist the stupid. Estimated theta, horizontal displacement, x or vertical displacement y. So yeah, that's easy. You make a shot. So you just like make a shot of this gentleman, and just into the mid journey try to generate the different representation of this gentleman. Now they just try to if this is a form. So this is normal form. Is do the rotation, we do the horizontal translation and the vertical translation. So I input. So when we train this is image. I give you the theta and x and y representing how much has been rotated, and how much it has been shifted horizontally and vertically. So there's a so finally so what is the input? The image, right? What is the output? Theta, x and y. Do you get it? So each picture has been told. This is ground truth. We understand how much has been rotated and how much has been shifted in x and y. So this is theta x and y. So this is the input. Output is a theta x y. Right. Okay. So yeah, good quite. this. 000, this is Osaka. This is orthodox. So it has been transformed and has been rotated and shifted a little bit. And this is shift a little bit to the right. And then there's the input, the PCB image. Finally, we do the prediction. So what is the output? So say that XY is a real number. So it is a regression. It belongs to the regression, not classification. Okay, so I think I should let you go. This is this is good enough for today. And there is something, the code. Yeah, this is a code as well. This yeah, there's the same. This is only for your reference. I'm gonna skip it, so I'm gonna stop here. I think I finished this slide for today. I will turn my attention to the textbook next week. Okay, any questions so far, ladies and gentlemen? I hope you can submit your report next week, I hope. However, if you really think you need more time, just let me know. All right, I'll see you next week. Thank you. If you have any questions, just align me. Yep. Thank you.